Hi class, part 4 of queuing, waiting in line, and final video. So for the final video, we're going to look at two very different models. One is very, very different, and the other one is a little bit different. So the first one that we're going to look at is the no waiting in line model. We are going to assume, I'll get to this in a moment, we're going to assume Poisson arrivals, so it's M. We're going to assume arbitrary service time, so there's a G, K because it's a multiple serve system, so there's going to be multiple servers. But there's something interesting here. There is no waiting in line, meaning you're not allowed to wait in line. What does this mean? That we're going, if you come to the supermarket and you get there in line, we're going to beat you up? No, it's just for some very interesting systems out there that waiting is not a possibility. So where this came from, and there's still some today, they exist, but where this came from, it actually goes back to the origins of queuing theory, which I didn't spend any time at the beginning telling you. I don't think I did. So queuing theory was developed by an engineer, a telecommunications engineer who worked in telephone lines. I think it was in very early 1900s. Very early. I was trying to think of the year that he came up with this, but I cannot remember if it was but it was a very early between 1910 and 1920, something like that. And back then and still today, in a sense, when you make a call. Well, why did he develop queuing? He developed queuing because he was looking at the waiting times that people were waiting to get connected, right, when they were making a call, how long it took for the connection, how many people were in the system waiting because the system was limited, the capacity, and so on. And if you ever made a call to a landline, if you are old enough to have had that experience, you can get a busy signal. The busy signal means you're not in line. So the other party is busy, talking to someone else, and they're not going to pick up your call. You get a busy signal. And that means you are rejected from the system. You don't get a signal and then you're picked up later that's it, you're done. Then later of course came the call waiting, right? So you could actually be waiting in line for the other individual to pick you up, right? And today with more modern communications, obviously I don't think people even know what call waiting means, but is what we have today, right? You don't get a busy signal unless there's got to be something out there that gives a busy signal. I just don't know exactly what it is. So that's what we're talking about, okay? You're not allowed to wait in line. You get kicked out. So here's an example. We have several firms operating in the over-the-counter market. I'm not going to spend time explaining financial markets here, but that's one class that I also teach, but I'm not going to spend much time. But for example, just to give you an idea, the over-the-counter market, just to give you an idea, it's the Nasdaq. The Nasdaq is an OTC market. The New York Stock Exchange is not an over-the-counter system, but the Nasdaq is. And we have brokers wishing to trade stock for a client, and they're going to call these market makers at the over-the-counter. The market, I know I said I was not going to spend time, but the market maker is the individual who is at the remotely or physically, but they are part of the stock exchange, and they are the ones that marry the bids and the asks, the buying and the selling, in the market. So when you want to sell something, they go through them, and they're going to find you somebody who is willing to buy it, and they do the pricing and they make that happen. I'll leave it there. There's so much more to talk about, but I'll leave it there. But these are the people that do it, right? So we have the brokers who are sending the orders and the market makers who are processing the orders. If you call one of these market makers and the line is busy, you are just going to call another one. You're not going to wait. Right? So you get off the system and you try someone else. You won your order to be processed. So we have a situation like that, and we have brokers calling to execute every 2 minutes. So the calls are arriving every 2 minutes. We're gonna have to do something with the time. The time required to complete the transactions takes about 75 seconds. So the market makers, it takes them 75 seconds to, from picking up the call, talking to you, what do you want? This, okay, let me do it, and then hang up, is 75 seconds. The firm, this particular firm, has 4 traders. It always sounds like I'm saying trader. Traders staffing the phones. Let's assume that the calls arrive in a Poisson distribution, right? So they're just basically random. They just arrive, but they do arrive on an average of every 2 minutes. So you want to know how much business are we losing, right? Well, how much business is Richardson losing when somebody calls and they get a busy signal, right? That's money lost. They're not going to make the fees on that. What if instead of having 4 people, we went down to 3 individuals? How would that affect our business? How much business are we going to lose by doing that? No formulas for this one. Like the ones before. This one's a very special case. We're going to use normal distributions not in this case. We're not going to use normal distributions. I'm sorry, I apologize. I'm thinking of another example. We are going to use some of the formulas, but not all the formulas. You'll see what I mean in a second. But first of all, what you need to do is you need to convert everything to hours, because remember we had minutes and seconds. So I'm going to convert everything to hours, so we always have the same scale, if you will. So if the orders are arriving every 2 minutes, that means that we get 30 per hour. If the service time is 75 seconds, that means 0.013. So 1 over 75 multiplied by 60, that means that you get 0.8 per minute. And if you multiply that by 60, you get 48 per hour. This one is painful, right? Because you have to go back. You got to go from seconds to minutes to hours. But now we have them 30 per hour, 48 per hour service time. Okay, so we are going to use a PO formula. We're going to run the PO formula for K equals 4, and we get a PO of 0.536. Okay. Then we're going to use the P4 formula, and there's a formula for this in this case. Remember, this is the Poisson arrivals with arbitrary arbitrary service time. You process that the number, and you get 0.03, meaning with 4 traders, you have a 0.3% potential that a customer is lost. What does so if you think this is like this, right? Imagine there are 4 people picking up the phone, 4 people. So the chances that when you call, none of those 4 people pick up the phone is 0.3%. Now, what happens if your K goes down to 3? If you only have 3 individuals, you gotta run your PO. What's the probability that there's nothing in the system? So that's gonna be 0.36, 0.37. Then you calculate a P3 instead of P4. Now you calculate P3, and you get 0.022, which is 2.2%. So with 3 traders, there is a 2.2% probability that when you call, none of the 3 pick up the phone. Now, I'm going to show you my Excel, because this is why I was getting confused earlier, because I was just thinking about, I'm always talking to you about the one that we're looking at, but I'm also thinking about the one before and the one after. Here. Okay, so this is the no waiting model. You see how different it is? Yeah, this way is very different. You're going to enter your arrivals, you're going to enter your service, you're going to enter the number of servers. So the base model, the base is 4. I'm going to put 4. All these numbers just populate, right? So Okay, this represents, let me show you the formula. Well, the formula, I built it in there. You don't have to worry about it. It's based on normal. It's based on normal distribution and other stuff. So you don't have to worry about that. This means that this column right here, probability of being blocked, represents the probability that 1 is going to block you, that 2 are going to block you, that 3 are going to block you, that 4 are going to block you. Yes, I only have it up to 4. So if you have, a system of more, you will have to copy and paste and, make a bigger model. It's up to 4 only. So this is the one that you are talking about. If we have 4 servers, what's the probability that all 4 of them block you? 0.0034. Okay, that's what we found out here. Am I going back? Oh. By the 4th video, I'm already losing it. Where's my one more? Okay, this one. 0.003, 0.0034. I have more decimals here. Okay. Again, this shows you the probabilities with 4 servers. With 4 servers, the probability that none of them will block you, that 1 of them will block you, that 2 of them will block you, 3. Remember, it's okay if it's 4 servers and 3 of them block you. That's okay, because the 4th one won't, and that individual picks up the phone. It's perfectly fine. So you're really interested on this one. Right? With a 4 server, you're interested in number 4 because what's the probability that all of them block me? 0.003. So it's 0.3%, 0.34%. That's very, very, I don't know, I think it's pretty good. So now we're going to go up here. Same numbers for everything else, but now the system is going to be a 3 server system. So I'm going to go from 4 to 3. I'm changing this to a 3. The numbers change. You're like, no, they didn't. No, they did, but just a little bit, but you see. You look at this table, but this is how you read it. Now in a 3 server system, what's the probability that all of them block you? Well, you're not going to look at this number 4. You don't look at that number. You look at this number. In a system of 3, what's the probability that all 3 block me? 0.0219, which is 2.2%, which is what we calculated, manually. That's how you do it. Okay, so you have to remember when you're doing this that when you change this number, you're looking at a different row. Okay, so when you put a 4, you're supposed to look at this one. When you put a 3, you look at this one. Yes, the numbers don't change much. In this example, it just they really don't change that much. The numbers themselves. What changes is the answer because you go from 4 to 3. So instead of looking at this row, you're looking at that row. And here what I did is I just did, it's a very simple math. All I did is 1 minus this. So this is the probability of being served. This is the probability of not being served. This is the probability of being served, which is going to be 1 minus this. Just, from your probabilities in chapter 3, right? Just very simple. So now this is the time where you have to think. Let me go back here. So with 3 servers, you could lose 2.2% of your customers. With 4 servers, you can lose only 0.3. So there's a difference of 1.9. How much is that worth to you? So I could give you all that data, right? I could tell you exactly how much you make per customer. Then you can calculate how many customers you lose per hour. You multiply by how much money you will make per customer, and then you figure out, how much. 1.9% of that will be the total of money that you're losing, and then you will compare it to hiring another employee. And if the hiring another employee it's lower, then you will just hire the employee and get that revenue. All right. Final model. The final model is a finite finite calling population. And I gave you an example in the previous video, if I recall correctly. I gave you the example of a plane, right? A plane, you sell 250 tickets, so you know that the more tickets you process, the more people you board on the plane, the shorter the waiting line gets. Always, right? Because you cannot add more people to that waiting line because it's a finite population. You only sold so many tickets. Think of a stadium, right? The Patriots. If you sell 60,000 tickets and people start coming in to get into the stadium with their tickets, you know that as every individual that comes in, right, you're not gonna get an extra individual waiting in line because it's a finite population. Once they all go through the system, it's over, it's done until the next game where it all starts again. So here's an example. This is an example of an amusement park. It's actually a very interesting example. So we have Biff. Biff Smith is our maintenance. He's in charge of maintenance, and he maintains 4 of the rides at Rollorama Amusement Park. So Biff is the maintenance individual. There are 4 rides that Biff has to take care of. So he's the only individual. It's a single server, right? Only one individual is going to take care of those 4 rides. And on average, each ride operates for 4 hours, and then they need to stop them for maintenance. This reminds me a lot of aircraft in general, but aircraft in the military. But anyways, so they stop the ride, and Biff comes in and he does the maintenance, whatever maintenance it needs. Each ride is gonna use a different amounts of maintenance, right? It could be a big ride or a small ride, whatever, But on average, it takes 10 minutes to do that maintenance. I don't know. Sounds like Biff is pretty good at what he does. So every 4 hours, each ride shuts down. Biff comes in, and on average, after 10 minutes, he's done, and he can go back in line. The ride can go back on, and people can enjoy it again. So we're going to assume in this example, we're going to assume that we have exponential distribution for the maintenance itself, which makes, like I said before, some may take a little bit, some may take more, and it could be exponential. And I believe we're going to assume Poisson in this case. Yes, we're going to assume Poisson as well. Meaning, this is not the arrival of the individuals at the park or at the ride. This is the arrival of the machines. Every 4 hours of operating, when the machines operate for 4 hours, they go for service. So they can randomly come in if some machines are being used a lot, some machines are not being used as much. So they're coming in randomly. So that's why we're using Poisson and exponential with one server. Okay, we're going to take all of our numbers. We're going to turn them into hours because we had minutes. We had minutes here, there. Yeah, we're going to turn everything into hours. So the arrival is about 0.25 per hour. So every 15 minutes, one machine goes down. And Biff can process 6 maintenance jobs per hour. Okay, so we have a ratio of 1/24 of those 2. All right, so the first thing that you do is PO, and you will take the formula from the MM1 system, because that's what we are applying to this finite. We have decided that this is what it looks like. So you apply your PO, and you get 0.841. So that's 84% of the time. There is nothing in the system. PO means how many customers, in this case, we're talking about the rides, how many of them are in the system, and in this case, it's 84%. So Biff doesn't seem to be working very hard. I don't know, that's maybe unfair. Maybe Biff is working hard, but he sure has a lot of time to just do nothing. we have all the other formulas that we can use, and we can continue processing. So for example, what is the average time a ride is down for minutes? This is crucial. This is really, really important, right? Because when the machines are down, you're not making any money, and you want the machines to be operating so you can sell tickets and make money, right? Same thing with airplanes. When an airplane is for an aircraft, any type of aircraft, or if you're in the military, an airplane that is in maintenance is not an airplane that it's can be used for combat. So that's a problem. You want to minimize that. Sorry, I was going to go on a tangent with military planes. No, I'm not going to. So you want to reduce that because there's a cost. You're not making money, or it's not what you're in business for. So we need to care for that. So we're going to process all those numbers, and we're going to get a 11. Your W, remember you need to do all of them, LQ, L, W, Q, W. So your W is 11.3 minutes. So your machine, these rides, these rides on average go down for 11.3 minutes. It actually sounds very good. This example is kind of silly because it sounds very good. But if 11.3, so what will you do here, right? How many tickets do you sell per hour, per minute, or per hour? You can do the math. How many do you sell? Well, there's 11.3 minutes that you're not selling any. How much money does that represent? How much money would it cost you to hire another BIF so the rides could go back on maintenance? I'm sorry, back on operation. They could be operational. In less than 11.3 minutes. You can calculate that. Do all that math and figure out whether or not you should hire another BIF or another. I'm taking it too far now, but you will look at the rides and like, okay, they're going down every 4 hours. Are there any repairs that I can do? Any upgrades, not a repair, any upgrades that I could do to the rides? So instead of going down every 4 hours, they go down every 5 hours or every 6 hours of operation. We definitely with aircraft, we care about that, right? We use better materials, et cetera, so they're down for a much shorter period of time. And that is it. That is the end of this chapter on queuing, on waiting lines. Thank you. Sorry, I forgot to show you before I finish. Sorry, I forgot to show you the Excel file on this one. Okay, here it is. So now you have 4 inputs in this system. You have the number of servers, BIF, arrival rates, service rates, and the population size. So you enter all of that into the Excel, and you get a PO of 84%. If you remember, that's how. What is the probability of nothing in the system? That's equal to BIF's idling time. But we're looking for W, which is what's the average time that a customer spends in the system. So how long are they down? So it would be 0.1883, which is of an hour, which if you calculate in minutes, multiplied by 60 is 11.3 minutes. Okay, so that's it. That's the end of that.